Hello, everybody. Today, we're going to talk about a number of problems in the GMAT that have to do with the topics of motion, word, and mixtures. These three topics are more broadly categorized as word problems. Word problems meaning you have problems that have a lot of text that you need to interpret. Okay, using formulas or equations. Let's begin with the first of these topics, motion. Motion problems can be solved with the following formula, which is the distance run equals the product of the speed multiplied by the time taken to run that distance. So you can see here, there's a short scheme, right? If there is, for example, some motion in two different spans, each span having a different distance, and the mobile can run this distance in the first span using a certain speed, S1, but once it arrives at the point B, it changes its speed to speed S2. And so using this distance, it will run the distance between points B and C. Evidently, in each of the spans, it can also take a different time. So, for example, in this scenario, you can calculate the average speed for the whole motion as the total distance divided by the total time. Okay, it's a rate. You need to calculate the total distance divided by the total time. Okay, so for example, in this case, the total distance would be distance 1 plus distance 2 divided by time 1 plus time 2, right? You have to use this formula only when the question asks for the average speed in a motion that is done in 2 or more spans. Okay? So let's see an example. A car traveled 120 kilometers from city A to city B at an average speed of 40 kilometers per hour. Upon arriving to city B, the car traveled to city C a distance of 120 kilometers at an average speed of 60 kilometers per hour. Question says, how much longer did it take the car to travel from city A to city B than to travel from city B to city C? Well, it's basic for most of these motion problems to actually do a sketch. Okay, here on a line segment, I draw all the endpoints and intermediate points of this motion. So cities A, B, and C. Now, we know that the first span is 120 kilometers from cities A to B. From city B to C, that is the same distance again, 120 kilometers, right? Here and here. What about the speeds? In the first span, they mentioned there was a speed of 40 kilometers per hour. In the second span, there was a speed of 60 kilometers per hour. What about the time? Well, we don't know the time for the first span, nor the time for the second. But how can we calculate the difference in the times taken to run both spans? Well, what we actually need to do is calculate T1, okay, which would be the distance in the first span over the speed in the first span. So that is 120 divided by 40, that is 3. Units are hours, right? So 3 hours. What about the second time? The time for the second span. That would be 120 divided by 60, which is 2 hours. All right? So what's the difference, right? How much longer did it take the car to travel from city A to city B? You just do this difference, right? T1 minus T2, that would be 3 minus 2 equal 1 hour. And that would be the answer. Now, what was the average speed for the entire trip? Well, from our formula, we know that the average speed is the total distance, so 120 plus 120, divided by the total time. But we know the total time from the first question. We calculated 3 hours plus 2 hours, right? It's the total time taken for a whole trip. So this is just 240 divided by 5. Okay, here is a 2, here 1. 24 times 2 equals 48 kilometers per hour. You can see actually the average speed here, it's like the kind of weighted average of the speeds, since it is closer to 40, slightly closer to 40 rather than to 60, right? It's not the simple average, it's more sort of weighted average. The average speed of a motion in two spans. So let's continue with some other patterns. In some of these problems, you will be asked to transform units like miles, kilometers, hours into minutes, etc., or feet to inches, right? Some of the conversions that you need to do are obvious. For example, 1 minute, is 60 seconds, so converting minutes to seconds is very easy. But the ones that are not obvious, they will be given to you, right? For example, how many hours does it take a car to travel 3 miles at an average speed of 52.8 feet per minute? Knowing that the equivalence between a mile and feet is 1 mile, okay, stands for 5,280 feet. So let's address this question. How many hours does it take a car to travel 3 miles at an average speed of 52.8 feet per minute? We know here the distance is 3 miles and the speed is 52.8. So the time we don't know, but the time is basically the distance divided by the speed, 52.8 kilometers, feet per minute. So we need to do a conversion here, since there are miles and there are feet. We can convert miles into feet. So here we would multiply the quantity of miles by a conversion factor, which is a rate, okay? 5,280 feet per 1 mile. Below, we have just 52.8 feet divided by minute. Okay, here, miles and miles go away, and we have 3 times 5,280, right? Divided by, and the feet with the feet go away, okay, divided by 52.8, okay, and the minutes here will go up, right? So we simplify this, okay? If I divide by 52.8, I just get 100, right? And here, we just cancel this. So in the end is 300 minutes. Now, all we need to do is convert the 300 minutes into hours, which is 1 hour over 60 minutes. This is our conversion factors, minutes. So here, we just do the math. 300 divided by 60 is 5. So totally 5 hours. That's the answer. Okay, so you can do the conversions using the conversion factors, which are actually rates, right? Fractions, on the numerator, you can put one of the units, and in the denominator, you can put the equivalents, okay? Let's see another type of problem, which is a problem with two objects traveling towards each other. In the first case, you have two moving objects that depart from opposite directions, but they travel, toward each other, okay? It's like they are meant to collide or to meet in some intermediate point. So let's say that we know that two mobiles depart from opposite points, separated by 28 kilometers, and we know the speeds of each mobile as 3 kilometers per hour and 4 kilometers per hour. So basically what we're doing here is this, okay? To estimate the time, okay, in which these two objects will meet in the middle will be the original distance that separates them at the beginning of the motion divided by the sum of the speeds. Like this. So that would be 28 divided by 7, right? And kilometers go away, we have 4 hours. Okay, so in general, when it's about two objects traveling towards each other, okay, so you have that the time for meet up. It is just the distance that separates them at the beginning of the motion divided by the sum of the speeds of the two mobile objects. Okay? On the other hand, if we have two objects traveling in the same direction, one after the other, and the one going after the first, it is actually faster than the first. So it's like a pursuit, okay? Let's see here two objects at these speeds, and the original distance separating them at the beginning of the motion is 33 kilometers. So in order to find the time that will take mobile A to catch up with object B, you just need to divide the original distance separating them by the difference of the speeds. So this here would be 33 kilometers divided by 3 kilometers per hour. Kilometers and kilometers go away and the hours go up. So it's 11 hours. So in general, the time for catching up for one mobile going after another, it is the distance separating them at the beginning of the motions divided by the difference of their speeds. Okay? So that would be another typical problem of motion. Well then, let's now put together all this theory and let's review a few examples. It says Paul runs from his home to the grocery store at an average speed of 8 miles per hour and then walks home along the same route at an average speed of 4 miles per hour. If his whole journey took 45 minutes, how many miles is his home from the store? Well then, let's graph this all together. right? We can imagine that there is the home of Paul, then he has to arrive at the grocery store and then go back home, right? Using the same route, but we just put it this way so that we can see all the motion parameters clearly. Okay, so in the way to the grocery store, he had to cover a certain distance. We don't know. Actually, that is the distance we want to know, right? And he covered this using a speed of 8 miles per hour. He probably took a certain time. We don't know. We could just time for go. And from the grocery store to his home, he covered the same distance going back. But this time, he went slower, right? More slow, just at 4 miles per hour. And evidently, the time for returning from the grocery store to his home, we also don't know. So, what we are told is that the time for going to the grocery store and the time for going back home is in total 45 minutes. But in order to use this expression as the base of our calculation, let's keep track of the units here. We're talking about miles per hour, and we're talking about minutes. So we either put the time unit in terms of hours or in terms of minutes. Let's say we use just hours. So this would be 3/4 of an hour. Okay, but the time to go to the grocery store can be expressed as the ratio of the distance divided by the average speed in the first span. All along, the time to go back home will be the same distance divided by the speed he used in the second span on the way back home. It's the distance divided by 4 miles per hour. And this will be equal to 3/4. So now what we can do is just factor, right? Or multiply everything by 8. So it will have d plus 2d equals 3 times 2. And that would be 6. So from this, we know that the distance is actually 2. Okay? And that would be the answer. All right, let's see another example. Paul is driving in a straight track heading east at a constant speed of 52 kilometers per hour, and he passes certain street lamp. Half an hour later, and traveling in the same direction, Peter passes the same street lamp while driving at a constant speed of 76 kilometers per hour. If they both remain in the track and maintain their speeds for at least 2 hours, how long after Peter passed the street lamp did he catch up with Paul? Well, this key expression in the question reveals the problem is about the time of catch-up. For two mobile objects in motion, right, and one going in pursuit of the other. So, let's graph this. We have here this situation. There is a certain street lamp on the way the vehicles have heading east, right? And you know, at some moment, Paul passed to this point, and then he continued his way, running at 52 kilometers per hour. Then, half an hour later, Peter also passes through the same street lamp. And he goes faster, 76 kilometers per hour. Evidently, in that half an hour, right, Paul has been able to run a certain distance. Okay? And then we're asked, how long after Peter passes the street lamp he catches up with Paul. So we're trying to estimate what is the time for both of them to come together, right? To come together and Peter catching up with Paul. So we want to know that time. And we know that the time for catch up equals the distance that separates them divided by the difference of their speeds, 76 minus 52. And so here we have just the distance divided by 24. But what is the distance that separates the mobile objects when Peter passes the street lamp? Well, you can think about this. The distance Paul covered, in those 30 minutes would be commanded by the formula times multiplied by speed. That is to say, half an hour multiplied by the speed, which is 52 kilometers per hour. So this is 26. So now the formula is complete. 26 divided by 24 equals 13 over 12. And that is 1 unit and 1/12 of an hour. So this is simply 1 hour and 5 minutes. Okay. So the answer is option 2. All right. It's always useful to make some sketch where you can quickly put all the relevant information given to you in the problem. Let's do one more. A car travels from town A to town B at an average speed of 75 kilometers per hour, and then from town B to town C at an average speed of 50 kilometers per hour. The car didn't stop at town B. What was the average speed at which the car traveled from town A to town C? All right, if we graph this, we have the following, right? We have town A, certain town B, a certain town C. In the first span, okay, there is some distance, I don't know. I know the speeds, 75 here, and here 50. And, okay, here you have, there is a time in each of the spans. So, what do we want to calculate is the average speed, which is the total distance divided by the total time. All right, so let's see what we can do. The first statement says that the distance a car traveled from town A to town B was 3 times the distance that car traveled from town B to town C. So here's interesting. You have that the time 1 on the first span is actually 3 times the time 2 in the second span. So we do this, right? The average speed then would be the total distance, which I can actually express as a product, is the sum of these two distances divided by the sum of these two times. So let's say that we can express, right, the time 1, right, and the time 2 as a proportion. So time 1 over time 2 equals 3k over 1k. So what about if I express the distance in the first span as the product of the speed, 75, multiplied by the time in the first span? And distance 2 would be the speed multiplied by the time 2. But notice what is going on here if we replace everything in terms of these equivalences using the auxiliary constant k. So it would be 75 multiplied by 3k times 50 multiplied by 1k divided by 3k plus 1k. So you can see you can quickly factor the k's and cancel. So what yields is a unique value, and that would be sufficient to answer the question. Okay, statement 2 says that the amount of time that it took the car to travel from town A to town B was 2 times the amount of time that it took the car to travel from town B to town C. So the time 1 is to the time 2 as 2k is to 1k. So I can use here, the formula is distance 1 plus distance 2 divided by the sum of the 2 times, which would be 2k plus 1k. Now, distance 1 I can express, right, as the sum, right, or the product of speed and time. Okay. Oh, I'm really sorry. Here there is a mismatch. Here what we have is the proportions of the distances. So it's a distance 1 to distance 2. So actually what we should have done here, okay, is all the way around. Let's just go back a little bit. Because here, you have that the distance, right, 1 can be expressed as actually 3k plus 1k, the distance 2. And the times can be expressed as a quotient, the ratios of distance and speed. So that is to say, 3k over 75 and 1k over 50. We can cancel still all the case because you would have 3 plus 1, 4, and 3 75ths plus 1 over 50. And that would also give a value. So it's still sufficient. And what about in the statement 2, you have distance 1 plus distance 2. We can express now the distance as the product of the speed times multiplied by the time in the first span, that is 2k, according to this equivalence here, right? So the distance 2 would be the speed multiplied by the time, which would be 1k. And the times added would be 3k. So you can see here that the k can be factored and canceled. So you would have 75 times 2 plus 50 over 3. That's also a numeric value, a unique value which stands for sufficiency. So the answer choice would be okay. So that's it for the motion examples. Let's now go back to the theory of work. Work problems are similar to motion, actually. But instead of distance, we use the concept of work, which is another way to say that the definition of rate or productivity, it's the amount of work that a certain machine or person can perform or do in a certain amount of time. So when you are told in problems that 2 or more persons or machines are working at the same time on a job, we can add the rates of these 2 machines or persons. So the sum of 2 rates multiplied by the time they work together equals the work they do together. You can express this in another way. You divide everything by the time. Now, here, if you take this and write it here, dividing work, then the rate of machine A can be expressed as the ratio of the work done by machine A divided by the time it takes this machine to complete that work. And the same goes for the rate of machine B. You add these 2 rates together and you have the work they did in total divided by the time they work together. okay? Remember that in most problems where they don't tell you anything about the work, they just talk about one job or one production lot, you just put 1 in the word. If they mention a fraction of a job, just put the fraction, okay? Let's see 2 examples. Maria does a certain job in 4 hours. So that means that Maria's rate is 1 job 1 over 4. That's the rate of Maria. Paul does 1/3 of the same job in 2 hours. So Paul does 1/3 in 2 hours. And they say that working simultaneously, in how many hours can they do twice the same job? Since they're supposed to be working simultaneously, I can add the rates of Maria and Paul individually, and I would get the work they did together, which is here twice the same job, that means 2 jobs, divided by the time they work together. So we can just isolate time. Here it would be 1/4 plus 1/6 cross product, that is 10 over 24, which is 5/12, and that is equal to 2 over t. So from here, t is 24 over 5 hours. That's it. Okay, so that's how we use the concept of the addition of rates for machines or people working simultaneously. Another example, Bob does a certain job in 4 hours, so its rate is 1 job in 4 hours. Carl does the same job in 6 hours, so Carl works 1 job in 6 hours. If Bob and Carl do the job together at the same time, okay, what will happen here? If they did the same job together, that means they are expected to do the same job and they would do it in a certain time. Let's find this time. And here it says cross product, that is 5/12. And so here, the time they take to do the same job together is 12 over 5 hours. But here, the question is not that. The question is, if they did the job together at the same time, what fraction of the job was done by Bob? So in order to know the fraction of the job, we need to use this time. We can propose a simple proportion, right? You can say, okay, if Bob does one full job in 12 over 5 hours, oh, sorry, it's not 12 over 5 hours, in 4 hours is what the problem says. He does one full job all along in 4 hours. So he would do X of a job, a fraction of a job in 12 over 5 hours. So it's just a direct proportion, right? 1 is to X as 4 is to 12 over 5. So this would be X equals 12 over 5 divided by 4. Simplify, you get 3/5. So that is the fraction of the job contributed by Bob. Since he's the faster worker, so he will be doing the bigger fraction of the job. Let's now continue with the concept of few examples, right, for work. Machine A can complete a certain job in 3 hours, that's question 2. If machine B can complete the same job in 5 hours, how many minutes will it take both machines working simultaneously to complete 2/5 of the job? All right, so what's the rate of machine A? Machine A works 1 job in 3 hours. Machine B does same job in 5 hours. So if we add the rates, we have, right, multiply by the time they work together simultaneously, I can get the total work they're expected to do, which would be 2/5 of the job. So let's do the math. Okay, the sum of this is 8 over 15 multiply by t. So we can just simplify here. 5, here you get 3, 2, you get 4. Okay? So, what is this? 4/3 of t equals 1. So t, the time would be 3/4 of an hour. That is 45 minutes. All right, let's keep moving to the same example. Question 5. Two machines A and B working together can complete a production lot in 5 hours. If the rate of machine A is doubled, both machines can complete the lot in 4 hours. How many hours can machine A alone complete the job? Okay, we can formulate here two expressions, right? The rates of machine A and machine B, if we add them, because they work together, they can complete one lot in 5 hours. Right? If we double the rate of machine A, that means 2 times the present rate of machine A plus machine B, they could complete one lot in 4 hours. So if you just multiply this by -1, right? You just get here minus RA minus RB equals -1/5. Add the two of them. Here you just get 2 over RA plus here just go away. So 0 and then 1/4 minus 1/5. So this is just, here I need to clear this. And here would be 1/20, right? So if the rate of machine A is 1/20, this means that it does one job in 20 hours. The answer is 20. One more example. We can use also the concept of rates to work out problems that have certain activities being done in time and being done at different rates. So we want to combine the aggregation of all those activities. You can just use the concept of simultaneous work. It says, for example, water is pumped into a partially filled swimming pool at a constant rate of 10 gallons per minute through an inlet pipe. At the same time, water is pumped out of the swimming pool at a constant rate of 10 gallons every 2.5 minutes through an outlet pipe. At what rate in gallons per minute is the amount of water in the swimming pool increasing? Okay, I can say the rate of ingressing the water plus the rate of taking out the water of the swimming pool should be the total amount of water, right? Let's call that W, that the swimming pool is increasing in 1 minute, because we want to know that. Okay, so what is the rate of ingress? That is 10 gallons divided by 1 minute. On the contrary, what is the rate of water coming out of the swimming pool? Well, it is 10 gallons over 2.5 minutes. But notice that here, although this is a sum, this is a sum with a sign, different signs, because while water is being pumped out, also through the other inlet pipe, water is being pumped into the pool. So these two, like efforts or amounts of work, are opposite to each other because they work in different directions. So it would be, you know, very sensible to actually put a negative sign to that rate. So here would be 4 gallons per minute minus, sorry, 10 gallons per minute minus 4 gallons per minute. And that would be 6 gallons per minute. This is W over 1 minute. So the answer is 6. That is it. All right. So we can also use the concept of work when we work with rates of activities that are performed in time, at the same time. Let's move back to the concept of mixtures. Well, mixtures are problems where you have to calculate the way that several liquids can combine to form a mixture. And usually these liquids are described as containing a single common element that is dissolved, right? Could be sugar, could be soap, it could be anything. And then you are given the concentration rates or percents of the common element in each of the liquids, and you're given the volumes of the liquids, and you have to estimate what is the concentration in the mixture. It's like an average concentration, right, of the common element. So in this example, we could calculate this in two ways. We could consider that the new concentration in the mixture is actually the weighted average of all the concentrations, where the weight for each of the concentrations would be just the volume of the liquid. For example, here we multiply 25% times 4, which is the number of liters, for example, 40% times 5, 100%, that's the concentration, it's pure. For example, it could be a sugar solution, just pure sugar, right? Multiply by 6. And this divided by the sum of the weights, which would be the total volume of the mixture, that is 15, would give you the average concentration. So if we do this formula and simplify, we get that 60% is the new concentration or the average concentration in the mixture. Another way to approach this problem is to understand that the common element dissolved in all the participating solutions, well, the amount of that common element must be fixed, no matter if you measure or count the amount of that element before the mixture or after the mixture. So the sum of the parts of this common element at the beginning, before the mixture, should equal the total sum of this common element at the end. So for example, what is the amount of the common element in the first solution? It would be 25% of that volume, 25 multiplied by 4, right? Then in the second is 40 multiplied by 5. We just take away the 100. 100 multiplied by 6, and this should be the actual concentration, right? Which is the percent multiplied by 15, which is the total volume, right? So if we just do that multiplication, a sum, we find also that X should be 60. Let's review an example. Solution X is a 40% chemical A and 60% chemical B by volume. Solution Y is 25% chemical A and 75% chemical C. If a mixture of solutions X and Y contains 30% chemical A, what percent of the volume of the mixture is solution X? Well, you can see here that, you know, what is the common chemical in both solutions that are mixing is chemical A in both of them. So we don't really need to care about the other concentrations of different elements in those solutions. We just care about the common solution or the common element dissolved in the solutions. So we know that the quantity, right? Let's say that there were X liters of one and Y liters of the other. So the quantity in percent, 40% multiplied by X plus 25% multiplied by y, that should be the same, right, as the percent of the mixture, which here it says contains 30% chemical A, and mixture solutions X and Y contains this. So it should be 30% multiplied by the total volume of that solution, which would be X plus Y. So what can we get from here? The proportion of the two weights, which is actually the volumes of the liquids. So here, 40x plus 25y equals 30x plus 30y. And here we have then 10x would be equal to 5y. And from this, x over y equals 5 over 10 or 1k over 2k. So now the question says, what percent of the volume of the mixture is solution A? This is the old question. What percent of quantity B is quantity A? We know this is solved by calculating the quotient A over B times 100. So let's do that. What is quantity B here? The volume of the mixture. So the volume of the mixture would be X plus Y. And quantity A, solution X, that is actually just X. So if we need to calculate this, we can do actually this, use the equivalence for X and Y in terms of the common constant K. So X would be 1K, X plus Y would be 1K plus 2K, 3K times 100, K's go away, and you have 100 thirds, that is 33 1/3%, and that would be the answer. Okay, so let's move on and do the examples for mixtures. Question 3. Two brands of liquid soap are to be combined. Soap X contains 20% glycerin, while soap Y contains 35% glycerin. If the combined mixture is to be 25% glycerin, what percent of the final mixture should be soap X? We can do this in the same way. You can see here, okay, that means 20% multiplied by X plus 35 multiplied by Y, that is the total amount of liquid soap, right, the glycerin, before the mixture, and after the mixture, you have 25% times the total volume. So from this, you can find the proportion of the weights. 25x plus 25y, then you go 10y equals 5x. So x over y actually is 10 over 5 or 2k over 1k. So now, what percent of final mixture should be soap X? Well, that is the volume of X divided by the mixture times 100. So if we replace the equivalences here, you have 2k over X plus Y would be 2k plus 1k, 3k times 100. K's go away, and 2/3, 200 over 3, that is 66 2/3%. That's answered. So it's all about finding the proportion of the two weights. Let's continue with exercise 6. A tank contains 1,000 gallons of a solution that is 5% hydrogen peroxide by volume. If 250 gallons of water evaporate from the tank, the remaining solution will be approximately what percent hydrogen peroxide? Well, it's interesting because here they say that there is a solution of hydrogen peroxide, but only water evaporates from the tank. So at the very beginning, there is, right, 5% hydrogen peroxide. So how much hydrogen peroxide there is, before the evaporation? Okay, it's 5% multiplied by, 5% multiply 1,000 gallons. That is the peroxide H2O2 before. But what about after? The peroxide after the evaporation would be a certain percent, X over 100, we don't know that percent, but of a different volume. Since 250 gallons evaporated, the total volume now is 1,000 minus 250. So, and this should be an equality. Now, take a look. 100 and 100 go away. You have 5,000 equals 1,000x. Here we can just first operate this, right? 750x. So if we do the division, x is 5,000 over 750. So here, go away, right? And here it is, take a division by 5, you get 15. Division by 5, you get 100. So it's 100 divided by 15. By 5, this is 20. By 5, this is 3. 20 thirds. That is 6 2/3. That is the percent, which is closest because it says approximately this value, 6.67. That would be the answer. So let's do exercise 9. 1/4 of a solution that was 18% sugar by weight was replaced by a second solution, resulting in a solution that was 22% sugar by weight. The second solution was what percent sugar by weight? All right, so let's have it clear. There is a solution, so it's a certain volume of a solution that was 18% sugar, okay? But we take away the 4th part of this, remove that part of the solution, so the remaining part is just the 3/4, right, of the original solution. And now we add the same volume we removed, but from some different solution. And this different solution, we don't know what exactly the concentration was. But we know it's just 1/4 of the original volume. And when we put together that volume back into the original volume, now it is a mixture that has a higher concentration of sugar, 22%. And that's the original volume again. So if we count, the amount of sugar before and after should be the same. Here, what is the amount of sugar in the first liquid? It would be 18% of 3/4 of a certain volume. Here, you have X% of 1/4 of that volume. And this should be equal to 22%, right, of the original volume. So these volumes go away, and so do the hundreds, and we get what? Okay, here 18 times 3/4 plus x over 4 equals 22. We multiply everything by just by 4, okay? To get rid of the denominators, we get 88 here. This is 18 times 3 is just 54, and 4 times x plus 4 is just x. So x would be 88 minus 54 equals 34%. That would be. So this method never fails, right? Counting the amount of common element dissolved in the participating solutions should be the same as the common element in the total mixture thereafter, right? So that would be the last example of this lesson. Thank you for your participation and see you in the next video.